traveling anywhere in the world. Use Google Map, we can find all routes from any one place to another place, and also can find the shortest route. I make a paper on this shortest route by algorithm known as discrete algorithm. I will show you later. In case of graph map, we can consider the places as vertices of graph and the route as a edge. Then the software of Google Map, when find the routes between two places, we can find the edges between these two places or vertices and also give the shortest edge as a shortest path. This this is this this is a destination vertices, this is a destination vertices, this is a starting vertices, and there is also many vertices v1 v2 v3. These vertices are the stations between one destination to another destination. Okay, and the direction, and the this road is a edge we consider. If our direction is from this green to this line, this is a direction and it is denoted by a arrow sign between this edge. Then the software of the Google Map, when find the route between two places, it find all edges between these two places or vertices and also give the shortest edge as a shortest path. This shortest path and the spanning part and the route between one destination to another destination is not a very small topic, it's a big topic and also very interesting also. Applications in internet. Yeah, nowadays internet is very important and vital use in a model sciences in working in a working techniques of internet. The concept of graph theory plays a very important role. In case of connectivity of internet, all the user are considered as vertices, and the connection between these two destinations is a edge. Then all internet user from a very complicated graph or data from one user to another user are shared through the shortest route in between them. Similarly, in case, I will show you my one paper. Uh, this is application of discrete theorem in wireless communication. This here I am using a discrete algorithm for finding the shortest path. I read this paper in a conference also. Now also I got the second prize. These are the applications of graph theory in internet from one application to another application. Uh, this Facebook to YouTube to Yahoo to Google, these all are the vertices indicate as a vertices, and the internet flow between this application to this is a edge. Okay, एक वर्टाइसिस के दो या दो से ज्यादा एजेस हो सकते हैं. Now we will move to a very important part, that is the application of graph theory in various branches of sciences. First of all, I will tell you the application of graph theory in chemistry. Chemistry graph theory is used in chemistry for mathematical modeling of chemical phenomena. We can make neutral model of molecules where vertices represent atoms and edge represent bonds. For example, this this H C H, these all are the vertices, and the bond between this H and C is edges, will be represented as H. There is a branch of mathematical chemistry called chemical graph theory, which deal with the non-trivial application of graph theory to solve molecular problems. The inventor of this chemical graph theory is Alexander Baban. Graph theory is also used, plays a very important role in biochemistry also. Applications in physics. Graph theory is also used in field of physics. Generally, concept of graph theory are used in different electrical circuit. Electrical circuit. These are the electrical circuit where this R1, R2 are the R is for edges and the corner. This four these corners are the vertices. The current voltage and resistance on the circuit can be drawn by using principle of graph theory. When we want to show throw of current in circuits, then we can use directed graph. Directed graph is suppose the current is flow from one vertices to two vertices. Then we can show that this arrow. Okay, so this is a direction of flow of our current in circuit. Then we can use directed graph. Also, we can connect the different physical process with the help of graph theory concept. These are the maximum number of branches possible in a circuit will be equal to the number of nodes or vertices. There are at least two branches in a circuit. These two are the fundaments of this electrical network graph. Okay, this is a circuit, and the circuit ka graphical representation. This is the graphical representation of this circuit. Applications in biology. Graph theory is used in many areas of biology. Graphs can be used in drugs target identification, determining a protein organ functions. The concept of graph theory can be also used in studying the structure of DNA and RNA. If we want to study the food chain of different animals in the ecologic system, then we draw some arrow diagram which represent the dependence of one sorry. Sorry. Yeah. The concept of graph theory can be also used in studying the structure of DNA, RNA. If we want to study the food chain of different animals in the ecology system, then we draw some arrow diagram which represent the dependence of one animal upon another for their foods. For example, we have this. This is the structure of DNA, structures of DNA. This is one DNA to another DNA to another DNA. These all are for vertices, and DNA transfer from one man to another is at edge. This is a food web in a forest. This, no? These are the if we want to study the food this diagram yeah, this food chain of different animal as we show na, this is the food chain of the animals for maintaining ecology system. Then we draw some arrow diagram. We represent the dependence of one animal upon the another for their food. This can also be considered the graph where the animal are vertices of the graph, and the connect then they must be connected if any of them dependent on their food. These animals are vertices, and the eating from one animal to another is a edge. Application itself, graph theory is also plays a very important role in mathematical itself. Graphs are useful in geometrics and topology, and such as theory of node, algebra. Graph theory plays a very important role in group theory, several fields of dynamic system, complexity, algebraic graph theory has been applied. A graph theory is also used in operation research of this is very important tool in OR. There is some OR problems can be solved with the help of this graph. In transportation problem, when we need to minimize the transportation cost or minimize the product, then the graph theoretical approach is very useful. It is also used in different assignment problems, such as assigning different pupils to different job, manage of timetable for school, college, assigning office, station, etc. Hello. Conclusion. Hello. Conclusion of this lecture is not actually is not the conclusion of this lecture. Conclusion of this episode, which is where I will tell you the application of computer science and sciences. Uh, these graphs are considered the best tool for modeling relationship between physical situation. Many real-world problem can be represented using graph. Different concept involved in graph theory and its application in computer science demonstrate the application of graph theory. The main aim of this lecture the main aim of this lecture is to present the importance of graph theoretical idea in various area of science and technology application for the researchers, and that they can be used principle of graph theory in their new investigation. Thank you. I also show I also have some beautiful result of graph theory in matrices form. Okay, matrix representation of graph. How we can how the graph theory can be represented in the form of graphical. First, introduction. A graph is a set of, as we know that graph is a set of edge and vertices can be, this graph can be represented in the form of matrices. Different matrices can be forms are, these are the different matrices, incident, adjacent, cut set, circuit, path, which is used, these matrices can be drawn in with the help of graph theory in graphical form. Incident. Hmm. Incident matrix. Incident matrix is a edge connect to our vertices is known as incident edge to that vertex. Just I will explain you in a one line only for this uh, lecture. If vertex is incident on vertex, then put 1 as it is 0. If a vertex is incident on a vertex, then we put 0. A of ij, this a of I is equals to 1, then we can is equals to 1, otherwise 0. For example, these are the set of vertices. This v1, v2, v3, v4, v5, v6. These are the vertices and edges. Edges are incident. This v1, two edges are incident on our vertex p. Na? And vertex 2, how many edges? A, B, C, F. Four vertices. Four edges are incident. In vertex 3, C, G, D are the three edges incident on a vertex 3. Okay? And so on. Vertex 5, and vertex 5, 1, F, F, G, E, H. These are the five edges incident on a vertex 5, and adjacent C only one vertex. As a vertex, such type of vertex here, a vertex C, only one edge are incident. If only one edges are incident, then the vertex is said to be a pendant vertex. Okay, this is the matrix representation of this graph. This is a graph. This is a matrix between vertex and edge, and this is edge A, B, C, D. How many edges? A, B, C, D, E, F, G, H. Na? And vertex V1, V2, V6. A, this A is incident on V1. Okay, and V1, A and B. So just A and B are 1, rest all are 0. See, all are 0. V2. V2 में how many vertices are under incidence? A, B, C and F. A, B, C and F write 1, other rest all are 0. Same. V3. V3 C, G, D. C1, G1 and D1. C, D and G. ठीक है, rest all are 0. Same V4, V5, V6. Adjacent matrix. Adjacent matrix I will use in my one of my paper, that is cryptography. Application of graph theory to store data by cryptography. This I will use a adjacent matrix in this paper, that is this is adjacent, this is graph, and this is the graphical, this is a metrical representation of this graph, and I use cryptography. Cryptography is a procedure of encrypt and decrypt data. This encryption and decryption algorithms, these are the encryption and decryption theorem. This is my interesting paper. If you want to read this paper, you got something new. Please, the actually adjacent matrix hota kya hai? If two vertices are connected by a single path, then they are known as adjacent vertices. The vertices is connected to itself, then vertex is said to be adjacent, and the vertex is adjacent. If two vertices are adjacent, then put 0. Otherwise, the result is 0. For example, this is the matrix representation of this graph. Okay, this graph, this is a matrix between vertex to vertex. Okay, if V1 is adjacent to V2 only, then it is 1. Rest all are 0. No other vertex are adjacent, other rather than this V2. The V2 is 1, rest all are 0. Same V2. How many vertices are adjacent to V2? That is V1, V5, V3. V1, V3 and V5. Rest all are 0. V3 to V3. This V3, how many adjacent vertices? V2 and V4. V2 and V4. And V5 also, no? V5 also. V5 is also equals to this. So this adjacent matrix is a matrix representation between vertices to vertices. That's circuit matrix. Circuit matrices is for circuit can be defined. Actually, circuit is a closed walk, which is starting and end point are same. Can be appeared with starting and end pointer. For example, this V1, V2, V1 A, V2 B, V1. This is a circuit. Circuit matlab what starting and end point of the vertices are same. ठीक है. Circuit contain, if not contain, is equals to 0. Circuit 1, how many circuit? First, D E J, D E G, ठीक है. First vertex, V3, V5, V4 contain. With CFG, CFG, another circuit is what? V3, V2, V5, again V3. ठीक है. How many edges are connected? CFG, CFG. Okay. And 4, 4 is for A, and this V1, V2, this is 1. Circuit 2 edges. First circuit DEG, DEGR1, rest all are 0. Circuit 2 CFG, CFGR1, rest all are 0. Similarly 4 and 5. So this is a matrix representation between circuit to edge and is known as circuit matrix by this graph. I will take only one graph, and with the help of this graph we will explain you, I will tell you incident matrix, adjacent matrix, path matrix, and many more. Path can be defined as an open walk in which no vertex and it can be appear more than one. If edge of graph is a part of given path, then put 1 as 1. This path of two vertices, yes, is equals to 1. If there is no path between Vj to Vi, then we can say that is equals to 0. For example, this path 1, A, F, J, A, F and J, A, F and H. One path is this. Second part A, C, G, A, C, G, H. But remember one thing, ki, there is no vertex is repeated. No vertex, no edges is repeated. Okay. That means starting and end point of the vertex are never be same. This is a matrix representation of path matrix, path and edges. Path 1, path 2, path 3, path 4, path 5. This at A, F, J, A, F and H. That is 1, rest all are 0. Same. Path 2, path 3, path 4, path 5, path 6. I will tell you my papers. These are my papers. This, these, I applying graph theory in physics and G functions also. G function special is a topic of special function. I apply this graph theory in this article. This is basically a paper related to a physics research, but I apply this graph. I apply graph in this research paper. Last month, this paper is published in one of the Scopus indexing journal. If you want, I will share the paper of link of this paper. Hello.
Yes, ma'am.
Now this is the end of actually it's not the end of this is the end of this lecture. Today I'm just explain you the very minor thing or very minor applications of graph theory, but this is very wide topic.
Yes, ma'am. It is very wide topic and you explain it very well. Thank you so much for your delivering such a insightful and engaging lecture on some application of graph theory in computer science and engineering. Your expertise and passion for the subject truly through, and we are grateful for the valuable knowledge you have shared with us today. Your comprehensive explanation and practical examples have provided us with a deeper understanding of the topic. Your research accomplishment and achievements in the field graph theory are truly commendable, and we feel privileged to have had that opportunity to learn from you, because as I study about yourself, you very awarded from the women research. That's very I think for women and for us is very uh, uh, insightful thing. So thank you so much once again. Now I would
Thank
like to,
you.
yes, ma'am. Now I would like to request all of you to please be continue like with this with us, because we have another session from another commendable speaker. Today there's two sessions, so one is over and second will start. Now Punika will hand over all.
So thank you, Anushka. We will wait a little till ma'am join. So, sir, shall I start?
Yes, Parth, are you there?
Yes, sir.
Okay, so the next speaker,
Yeah, ma'am is
get
there.
joined.
Yeah, Dr. Sana is there.
Dr. Sana ma'am, are you there?
Yes, sir, I'm here.
Okay. Welcome, ma'am.
Thank you, sir.
Okay, so Parth, you can start. Okay, so soon at 6 o'clock, the HOD sir will also will be in the meeting. Okay,
Yes, sir.
so we will
Purnika, over to
conclude the
you.
session, overall workshop.
Yes, sir.
Okay,
Yes, sir.
Yes, sir.
and yeah,
Yes, am I audible?
Purnika. Yes, Purnika, audible.
Okay.
You may proceed, Purnika, you may
Okay.
proceed now.
Okay, sir.
There won't be any video audio share screen lacks.
So after
Hmm.
this enriching event that we had, now we will go to yet another interesting speaker that I would like to call upon. So with a warm welcome to the last session of the day of the 5-day national workshop on applied mathematics and computing, organized by the Madhav Institute of Technology and Science, MITS Gwalior. Dear participants, we are honored to have with us today an esteemed speaker who will enlighten us on the topic domination in graph theory. Now, I would like to introduce our distinguished speaker, Dr. Sana Ejaz. She is a PhD scholar, mathematics with MSc B.Ed and presently working as an assistant professor in Department of Mathematics, Faculty of Sciences, Khaja Vandanabas University, Kalaburagi, Karnataka. She is a patient maths teacher with resourceful and engaging teaching style demonstrated over 12 years of academic experience. She has many research publications and has presented articles in different national and international conferences. Apart from all this, she has also organized 2 day state level interdisciplinary research workshop on applied mathematics and aerophysics and space sciences at Kalaburagi, Karnataka. Now, let us eagerly listen to Dr. Sana Ejaz as she takes the stage to enlighten us with her expertise and insights. Over to ma'am.
Good evening. Good evening to all the members
Good evening, ma'am.
and the people who have joined the workshop. I'm overwhelmed to give a lecture and give a talk. This is my first lecture actually after completion of my PhD degree. So I'll be sharing my throughout thorough knowledge of graph theory and domination, as my research topic is graph theory and in domination I have done my research. So I'm very much thankful to Atul sir for inviting me for this lecture. And shall I start the screen sharing, sir?
Yes, ma'am.
Okay. Is it visible?
Yes, ma'am.
Yes, ma'am. Visible, ma'am.
So here is my topic. I am Dr. Sana Ejaz, Assistant Professor, Department of Mathematics, Khaja Banda Nawaz University, Kalburgi, Karnataka. So my topic is domination in graphs. So here is the outline of the lecture. Here we are going to have introduction. In the introduction part, we'll see about the history of how domination exists in the graph theory, and we'll see few examples. Then we'll move on to domination definitions, and we'll also see few of the examples of domination through which the students will be able to easily understand the concept of domination in the graph theory. And we'll see domination bounds and few of its theorems and some of the domination definitions and few more examples on that. Then we'll move on to lemma and theorems, and we'll see the also we'll look into the applications of domination in graph theory. So we will start with the outline. We will start with the introduction. We'll first go to history part.
Sorry
So
to interrupt you,
domination,
ma'am.
pardon me, sir.
Sorry to interrupt you. Your PPT is not visible, ma'am. I think the mail site is showing.
Okay, that's first is only it's struck on the first slide, right?
No, no, ma'am. PPT is not visible.
Okay, sir. I'll start with the PDF. Give me
So
some
it is
time.
showing your mail.
Pardon me, sir.
It is showing your mail. Mail is showing, ma'am, in
Okay,
which
okay, okay,
some
okay, okay,
documents are there.
okay, sir.
PPTs.
Is this visible now? Is this visible, sir?
No, 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 ma'am. No, not yet. Share again, please.
Call Shayan. Sorry for the inconvenience, sir. Is it now visible,
Yes,
sir?
ma'am. Yes, ma'am. Fortunately, this time it is visible.
My voice is audible?
Yes, yes, clearly audible.
Okay, sir. So here I am Dr. Sana Ejaz, Assistant Professor, Department of Mathematics, Hajabanda Nawaz University, going to give a lecture of domination in graph theory. So here is the outline of the lecture. So we'll start first with the introduction part, wherein the introduction we will see the history of domination, how the domination has taken place, how the domination came into existence in graph theory, few of its examples. Then we'll move on to domination, its definitions, and we'll see few examples of domination so that students can make out and understand the clear concept of domination. Then moving to the next part, we will see the domination bounds, its theorems, some more definitions, examples, and we'll see books on domination theory. And moving on to the main important part of this lecture is the applications of domination in real life and in other streams. We'll also see the applications in this lecture. So here is the introduction of domination in graph theory. First, we will move on to the history part, how the domination has taken place, on what basis they have taken. Some of the mathematicians have understood the concept and they have introduced it. In 1960, the study of domination has actually begun. In 1862, C.F.D. Genick attempted to determine the minimum number of queens required to cover an n cross n chessboard. So this concept I'll show you through an example of chessboard. So here we can easily see the chessboard, and in this we can see every pawn or every component of the chess, how they are going to dominate the other components of the chess. Based on this part, based on this chessboard part, domination actually got introduced in the graph theory. So if the students want to actually see how domination occurs is, so they can just install a chess game app in their mobile phones, and they can see this type of part. This is very easily understanding. So if here is the queen, we can see, if we click on the queen part, we can see that how many chessboard it dominates. And it's the same goes with the other component of the chess. If we click on the other like camel or king, we can easily make out to which part of the chessboard it dominates to other components. So based on this n cross n chessboard, some of the mathematicians has introduced domination in graphs. So n queens problem, you can place n queens on an n cross n chessboard so that no two queens attack each other. The solution exists for all natural numbers n except 2 and 3. So this concept of domination originated actually in 1850s from a chessboard. So this problem determined the minimum number of queens that can be placed on a standard 8 cross 8 chessboard. So this also we can see through an example how 8 cross 8 chessboard. See here. Development of domination in graph theory, how it happens. Domination theory is an extensively researched subject in graph theory. Since a decade, we are learning this domination theory in graph. There have been extensively many research papers have been done in this domination topic, and it has different fields, different applications in the fields of arts, science, humanities. So when a problem appeared to determine least count of queens given a n cross n chessboard in such a manner that all squares are dominated. So as I have explained, so seeing this chessboard, we can easily make out which component dominates more, which component dominates to how many chessboard, and which component can attack the other components. So another important feature of dominating sets, the minimum dominating set. So here in this domination of graph theory, we will be having minimum domination set, maximum domination set as well. There may be also 6, 7 or 8 queens in a minimal dominating set. Hence the 5 queens constitute a minimum dominating set. So here in this graph, we can easily see, this is a graph. So here the red vertices, any graph will constitute of vertices as well as the edges. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices. And in these vertices, we can make out vertex 1, vertex 8 and vertex 9. These are the dominating vertices. See, we can see that 8 vertex dominates 7 as well as 3. 9 vertex dominates 4 as well as 10. Whereas 1 vertex dominates 6, 5 and 2. In this way, these 3 vertices dominates the whole graph. Excuse me, sir. I need water. So is the slide visible, sir?
Yes, ma'am, visible.
Okay. So with this graph, this is a graph wherein we can see the red vertices dominates the whole graph. So based on this concept, we can say that the minimum dominating set is contains 1, 8 and 9. I mean 1, 8, 9. This only 3 vertices dominates the whole graph. So 1, 8 and 9 vertices makes a dominating set. So minimum cardinality means the number of vertices in a dominating sets are 3. So here the minimum dominating set means a dominating set which contains the least number of vertices which dominates the whole graph. Next, move on to the history. Again, we can see that in 1892, W. Rose Ball reported three basic type of problems that chess players study during this time. That is covering, independent covering, and independence. What do you mean by covering actually? Determine the minimum number of chess pieces of a given type that are necessary to cover every square of a n cross n chessboard. So in the previous slide, we can see, so this particular queen can cover 1, 2, 3, 4, 5. This particular queen can, if we consider this queen as a vertex, then this vertex can dominate up to other 5 vertices. Means she can dominate other 5 vertices. It is connected to the 5 vertices. Means the covering number of this queen vertex is 5. Next comes to the independent covering. Determine the smallest number of mutually non-attacking chess pieces of a given type that are necessary to dominate every square of a n cross n board. It means that the independent covering, smallest number, which is non-attacking chess pieces. Which is non-attacking chess pieces is known as independent covering. In graph theory, independent covering means, as per this graph, I can explain, if one is a vertex which comes under independent covering, then it should not contain the vertices which is connected to one. We have to take such vertex which is not connected to this one. Means we have to leave this 6, 2 and 5, they are connected to 1. So if 1 comes under the independent covering, then we have to take either 9 or 3 which are not connected to 1. They will be considered as the independent set of vertices. Means those vertices which are not connected to each other, which are independent to each other. Independence. Determine the maximum number of chess pieces of a given type that can be placed on a n cross n chessboard such that no two pieces attack each other. It means that the independence number, determine the maximum number of chess given that it can be placed on n cross n. The same thing here. Independence means the vertices which are not connected to each other, which are totally dependent, will be considered as the independent vertices. Next, coming to the example of domination, we can see here n cross n board so that no two queens attack each other. So here it will be the one queen and here will be the one queen. They will be non-attacking to each other. There is currently no known formula for the exact number of solutions. Next comes to the domination part, which is the main part of our lecture. So in 1958, Claude Bourget introduced the domination number of a graph. In a graph G, a set S, which is a subset of V of G. Here, in any graph, we can see in any graph, there will be a set of vertices, which we call it as a vertex set. And there will be a edge set, which we call it as a E of G. So here, if we consider any set of vertices S, which will be a subset of graph, that will be a dominating set if every vertex not in S has a neighbor in S. Like seeing the previous slide, I can explain this. In this slide, we can say this. If 1, 8, and 9 are the dominating set vertices, we can see 1, 8, 9 is also a subset of this particular graph, and 1, 8, 9 are the dominating set. The dominating set definition explains the same thing. Is a set S, which is a subset of V of G, is a dominating set if every vertex not in S has a neighbor in S. So they should be neighbor to each other. It means that the vertex which we are considering in dominating set should dominate to other vertices. They should be in neighbor to each other. That is the main concept of domination. So here we denote this dominating set as gamma of G, and we call it as a domination number. It means that the minimum size of a dominating set, minimum size, or else you can also say the number of vertices, which we are considering in S, which we are considering in any dominating set, that number of vertices will be considered as the domination number, and we denote that as a domination number gamma of G. Its denotation is gamma of G. Everywhere in the research paper, we can see that gamma of G is nothing but a domination number. So we have many domination parameters what we have introduced in the last decade in many research papers. There are number of domination parameters with the different names: connected domination number, split domination number, strong split domination number, and many more such domination numbers. Those all domination numbers came after this invention, after this introduction of domination in graph theory. Next, moving on to the domination bounds. Here also I can explain the domination number through another type of graph. Here we have a Peterson graph. A Peterson graph, this is a Peterson graph. So here we can see that vertex 1 is connected to 0, 1 is connected to 2, 1 is connected to 5, whereas 5 is also connected to 6, 5 is also connected to 8, 4 is connected to 3, 4 is connected to 8, 4 is connected to 0. So here in this graph, we have to select such vertices which are dominating, which have the, or we can also say that we have to select such vertices whose degree is more. So here in this we can say in vertex 1 has only 3 degrees, 1, 2, 3. And vertex 5 has also 3 degrees, 1, 2, 3. So we have to select such vertices which has the degree more, which has the more number of degree. That will also be helpful to calculate the dominating set vertices. So here in this we can take such vertices which dominate the whole graph. So if we consider 5 in the dominating set, 5 connects to 6, it dominates 6, 6 came into this, 8 is also connected to 5, 1 is also connected to 5, so we can consider 5. So we have covered what? How many vertices we have covered in this 5? 1, 4 and 8. Next, what we can do, 1, 6 and 8 are already covered. Then we can take 3. In this 3 vertex, we have covered 2, 4 and 6. So in dominating set, we have considered 5, 3. So in this 5 and 3, how many vertices we have covered? 1, 4. We are left with how many vertices? 9. 3 vertices. If we consider 7 as in the dominating set, it will cover 6 as well as 0 and also 9. So we have to select such vertices, minimum number of vertices which covers the whole graph. So here in this vertex, we can take in this graph, we can take 5, 3 and 7 as the dominating set. So here the cardinality of our dominating set is 3. That is 1, 5 will be the one vertex, 2, 3 will be the second vertex, 7 will be the third vertex. So 1, 2, 3. So cardinality, I mean domination number will be 3. And dominating set will be 5, 3 and 7. Hope you all have understood the concept of domination number. See, in this again 3 and 8. 0 vertex has covered 4, 1 and 7, whereas 3 has covered 4, 2 and 6. 8 has covered 4, 8 and 9. Considering these 3's, 8 and 0, we have covered all the vertices of this graph. We can see 3 has covered 4, 6 and 2. 0 has covered 1, 7 and 4. Whereas 8 has covered 5, 4 and 9. So in this way, we have covered the whole graph. So 0 vertices. The Peterson graph has domination number 3. It means that the cardinality means number of vertices. What we are considering in dominating set are 1, 2 and 3. So domination number will become 3. Each vertex dominates itself and 3 others. So at least 3 vertices are needed. Since the graph has diameter 2, the neighbor of this diameter, the neighbor of a single vertex form a dominating set. So moving on to the next slide, here I have explained through standard graphs of cycles and path. Examples using cycles and path. So here we can see here cycle graph. We have C2 here, C3, all three are connected to each other. C4 graph, C5, C6, C7. And here path graph. Even we can draw a path graph like this, 1, 2, 1, 2, 3. It is not a closed graph. Whereas cycle graph will be a closed graph. All the vertices will be connected to each other. And in path graph, it will not be connected. It will be one after the other. Vertices will be connected to each other. Number, how we can find the domination number? So all we have to see that the vertices should dominate to more number of vertices connected to each other. I mean, if we consider 1 here, it dominate 4 and 2, but we are left with 3. So what we have to do? We have to even take 3 as also in the dominating set. So here are the exam. Here with the colored part, I have explained. So here is the C2 graph. So here in this C2 graph, only one will be the dominating vertex. One will be the dominating vertex. It dominates 2. And the domination number will become 1 here in cycle C2 graph. In cycle C3 graph, here we can see that 1, 2 and 3 are connected to each other. All 3 are connected to each other. If we take any of the vertices, it dominates to 3 as well as it dominates to 2. So here again for C3, domination number will be 1. Domination number will be 1. Why? Because the number of vertices in the dominating set is 1. So the domination number is 1. So next, moving on to C4. Here the cycle graph C4, all the 4 vertices are connected to each other. If we take one vertex which is connected to 4 as well as 2, there are 3 in the dominating set. It's not compulsory that we have to take 1 and 3 only. We can even take 2 and 4 also as the dominating vertices. So any vertices you consider, it's not compulsory that we have to take 1 or 3. Any vertices you choose such vertices which dominate more number of vertices too in the graph. So here one vertex is dominating 2 and 4, but it's not covering the number 3 vertices. So we are considering even 3 vertices. So the domination number for the cycle graph C4 is 2. Why? Because we have taken 2 vertices in the dominating set. So our domination number will become 2. Again in C5, we can see we are considering 1 as the dominating set. It's covering 5 and 2. The rest through 2 vertices are left over. So we are considering 4 vertex in the dominating set, and 4 comes under the dominating set. Whereas in C6, 1 and 4, here only 2 vertex is dominating the whole graph. In C7, we have 3 vertices which covers the whole graph, which dominates the whole graph. See, 1 is dominating 7 and 2, 4 is dominating 3 and 5. Then we are left with 6. So we have to take even 6 in the dominating set. So in C7 dominating set, we have 3 vertices, and the domination number will become 3. So gamma, we can see this is a path graph, not a cycle graph. This is a path graph. Actually, I have to write here P2, P3, P4, P5, P6, and P7. So this is a path graph. In this path graph, see, one is the dominating set. One comes into the dominating set. It dominates the graph. It's a simple graph of 2 vertices. So if we consider one in the dominating set, it dominates 2 as well. Now consider the second path graph, that will be P3. 1 is connected to 2, 2 is connected to 3. As this is not a closed graph, it is an open graph. So only 2 dominates 1 as well as 3. In C4 graph, if we consider 2, not considering 1 as the dominating set, if you want, by your choice, if you take 2 also, if you take dominating set as 2, it will cover 1 and 3, but 4 will be left over. So again, you have to take 4 as a dominating set. So the same thing goes with the P4. Domination number, anyhow, it will be 2 only. If you take 1 and 3, it will be domination number gamma G will be 2. If you take 2 and 4, gamma G will be 2. Same goes with the P5, P6, P7. Here the dominating set will be 2 and 4, and here it will be 2 and 5. Here it will be 1, 4, and 6. Not compulsorily you have to select these vertices in the dominating set. You can even select any other vertices also, but make sure the cardinality, there should be minimum number of vertices should be there in the dominating set. That will be considered as the dominating set, and the minimum cardinality only will be known as the domination number. So least number of vertices we have to consider. If you are considering here 1, 4, and 6, not 1, 4, and 6, if you are not considering this, even you can take 2, then we have to take 5, because we have to cover the whole graph. If we take 2, 2 will cover 1 and 3. Then we have to again take 5, it will cover 6 and 4. Then 7 will be left over. So we have to take 7 also in the dominating set. So 2, 5, and 7, again the domination number, that will be gamma G will be again 3 for P7 path graph. So here we can see gamma of Cn. Cn is nothing but a cycle graph. Gamma of Cn will be equal to gamma of Pn. It's a path graph. That means that domination number of a cycle graph, see, this is a cycle graph, domination number of a cycle graph is equal to domination number of a path graph will be equal to n by 3 of Cn and Pn. Both have a maximum degree of 2. It means that if they have a maximum degree of 2, then the gamma will be n by 3 of Cn. And therefore, each vertex can dominate itself and up to 2 other vertices. So if you can see for this theorem, this is just a basic theorem, first fundamental theorem we can also say. So gamma of Cn, take any of this cycle. If we take, suppose we take C6, gamma of Cn means gamma of C6. How many domination number we have in this? 2. So here gamma of Cn, gamma of C6 is 2. Whereas gamma of Pn, if we take gamma of Pn is also P6, then again for path 6 we have gamma as 2. So domination number for both will be same. N by 3 means what? We are taking n number of vertices as 6 here. 6 by 3 will become 2. So see here, we have 2 vertices. Domination number gamma is 2. Here also gamma is 2. So this theorem applies to all type of graphs, all type of cycle graphs and path graphs. Whereas cycle graph and path graph, n by 3 will be equal for domination number. Picking every third vertex starting from the second and using the last when n is not divisible by 3 yields a dominating set of size mod of n by 3. So suppose if we are picking n, after this, if we look into the matter, look into the higher number of vertices of in cycle graph or path graph, wherein this part is not applicable, but then we can take mod of n by 3 will be definitely be applicable. Now moving on to the next. theorem, next part of the slides, domination bounds. So whereas we have bounds in terms of different graph parameters, so here we have many graph parameters. We have bounds like upper bound and lower bound. In some research papers we see upper bound, and in some research papers we see lower bound. So here the set of all vertices is in a dominating set in any graph. Therefore gamma of G is less than or equal to n of G. This is the upper bound. This is the upper bound. What we do in the research papers is we will connect the domination number. We will take the domination number and we will relate it to the different other domination parameters, and we try to find out the bounds between them. We try to find out the number of vertices. We research with a type of standard graphs and other graphs, common graphs and other standard graphs. We take the different graph parameters and we try to find the bounds between them. We try to find the bounds between the gamma of G, like domination number, with different type of graph parameters. Now next, moving on to the other definitions of domination. So here, as I have explained in the earlier slides, domination number. So it's also a part of domination number. We have different domination parameters, as I have discussed earlier, like we have connected domination number, independent domination number, total domination number. These are the basic domination number. Recent studies have found out many more new graph parameters like co-total domination parameter, restraint domination parameter, Roman domination parameter. Those were in the recent studies. These are the basic one. What I am going to explain here, a dominating set S in G is a connected dominating set. Why it is known as a connected dominating set? We have a dominating set, right? So why they have named this dominating set as a connected dominating set? It means that this is a simple graph. We can see that this is a simple graph. It's a connected graph. It's not a disconnected graph. For any of the domination number, we have to consider only the connected graph. Only then we will be able to find the domination number and dominating set. So this is a connected graph. Here we can see that the red vertex is a domination number. It is dominating this vertex and also this vertex. Then these three vertices are remaining. So we can say, we can even take this vertex, it will cover this vertex and this vertex. Then why we have to take these two vertex, isn't it? Now next, if we take these two vertex are also dominating the whole graph. This vertex dominate to this two vertex are also this, and this vertex is dominating to this vertex. Here the graphs are same, all the three graphs are same, but in this all the three graphs we are considering the different vertices. Why we are considering the different vertices? In this graph we can see that this vertex is dominating this two, this vertex is dominating to this two vertex. But this is called a connected dominating set. Why? Because these two vertices are, first of all, they should be in a dominating set. They should be such vertices which dominates the whole vertex. And next thing what we have to see, that those dominating set vertices should be connected to each other. So these vertices, they are as well as dominating the whole graph and as well as they are connected to each other. That's why this is known as the connected dominating set. This connected dominating set parameter, minimum cardinality, we call it as connected domination number. We call it as connected domination number, and we denote that connected domination number as gamma of C, and the number is 2. See, we have two vertices in this dominating set, so domination number will become 2. That is gamma of C will become 2. Here this part, we can see that these two vertices are anyhow dominating the whole graph, but This vertex is not connected to this vertex. They are far apart to each other, but still they are dominating the whole graph. They comes under the dominating set. So this type of dominating set is known as independent dominating set. It means that the vertices which are dominating and which are not connected to each other, which are independent to each other, are known as independent dominating set. So here we have two vertices and the cardinality of these two vertices is 2. So independent domination number is denoted as gamma of I, and the number will be gamma of I will be 2. Gamma of I is equal to 2. Next comes here the total dominating set. Here in this total dominating set, we have to see that it should not have any isolated vertex. We have to consider such vertices wherein the graph should not have any isolated vertex. So this vertex is not isolated, it is connected to this, it is connected to this. And this vertex is not isolated, it is connected to this, it is connected to this. So here all the vertices, the dominating set, what we are considering the vertices in a dominating set, all have no isolated vertices. They don't have any isolated vertices in this graph. So this is known as total dominating set. In this total dominating set, the number of vertices are 1, 2, and 3. So this total dominating set is denoted as gamma of t, and the cardinality is 3. So we can say that gamma of t is equals to 3. Next, moving on to the examples again, we have seen this Peterson graph. In this Peterson graph, I'll explain how the total dominating set can be identified. So here we can see that 0, 4, 3, 8 are considered as a total dominating set vertices. Why we have considered this means, in total dominating set, as we have seen the definition earlier, the dominating set vertices should not be isolated. So here 0, 4, they are connected to each other, they are not isolated. Here 4 and 3, they are connected to each other, they are not isolated. 4 and 8 are also connected to each other, they are not isolated. So whereas in the domination earlier, what I have seen, if you go to the previous slide of Peterson graph, see here, if you see this graph here, in this 0, 3 and 8, this is also a dominating set, but we have not taken 4 into the dominating set. No doubt this 0, 3 and 8 makes a dominating set, and this is enough for us to consider in the dominating set. But for a total dominating set, the case is different. We should not keep any of the dominating set as isolated vertex. There should not be any isolated vertex. See, 3 is an isolated vertex. There is no vertex connected to him. Vertices which belongs to the dominating set should be connected to 3. So here what we are doing in this next part, in the dominating set part, here we have taken 4 into consideration of a total dominating set, so that 0, 4, 3, 8 all should be connected and there should not be any isolated vertex. So here in this Peterson graph, we can say gamma of t is equals to 4. The cardinality is 4. 1, 2, 3, 4 vertices are in the set. So we say that gamma of t is equals to 4. So here the Peterson graph has total domination number of 4. A total dominating set S must include a neighbor of every vertex in S. So here, since the graph is 3 regular, 1 vertex and its neighbor form a total dominating set of size 4. So here with this graph, I have explained how a total domination number can be taken into consideration, how the vertices can be considered. So for any type of domination sets, like maybe it will be a total domination set, maybe it be a connected dominating set or a independent dominating set or any other dominating type of sets. First and foremost thing is the set what we are considering, it should be a dominating set. Then again we have to see into the criteria of their connected, or whether they are total, or whether they are independent dominating set. So now moving on to again the cycle and path graph. Here also we can find out easily the parameters: connected dominating, independent dominating, and total dominating set. Sir, are my slides visible? Atul sir.
Yes, ma'am. Ma'am, it's
Okay.
visible.
Okay. So now moving on to the cycles and paths graph. In the previous slides, I have explained about the how we consider the domination number and how we see the dominating set. In this part, we are seeing the different types of dominating set, like connected, independent, and total dominating set. So in this cycle graph, these are the cycle graphs. Here we can see C6 and C7. Here are the path graph P6 and P7. In this C6 graph is a cycle graph. Here we can see I and 1 and 4, they are totally independent to each other. So here we can say that this comes under the independent dominating set. Here we can say that 1 and 4 are enough to be a dominating set. Since we have to make it a connected dominating set, what we are doing, we are taking into consideration we have to take the total dominating set. So we have to consider 2 as well as 3 into the dominating set. So to make it a total dominating set, we are considering 2 and 3 as well in the dominating set. So 1, 2, 3, 4 makes a total dominating set. So here same thing, this will be considered as the independent set, and this will be considered as connected dominating set. Like 1 is connected to 2, and 3 and 4 and 5 are connected. So this comes under the connected dominating set. So gamma of C will become 4 here. Here gamma of T will become 4 again, and gamma of I, that will is independent domination number, will become 2. Same with the P6 graph, path graph. Here gamma of I is 2, gamma of T is 4, gamma of again C is 4. So this looks pretty similar. These two type of graphs look pretty similar, but this one is for the connected dominating set and one is for the total dominating set. Same goes with the C7 graph, C7 cycle graph, and one more is the path. It means that P7 graph. P7 means the path graph which has 7 vertices. Here, this 2, 6, and 8 are considered as a into the connected dominating set. This should not be a graph. This is a normal dominating set graph. 2, 5, and 6. This is a normal dominating set, and here this graph is like 2, 3, 4, 5, 6. Here we are considering this graph as the connected dominating set, and this as the independent dominating set. Here we can see 1, 3, and 6. All the 3 vertices are independent to each other. They are not connected to each other. So we are considering 1, 3, and 6. Not necessarily we have to consider 1 and 3 and 6 only. We can even take 2, 4, and 7 as well in the independent set. But the cardinality remains the same for both the cases. Cardinality will be 3 for independent dominating set. So here is a connected dominant. 1 is connected to 2, 5 is connected to 6. So since see, this is the normal dominating set 1, 2, 5, 6. But here we are taking 1 as well as into consideration because we have to make it as a connected dominating set. So connected dominating set cardinality is 4. That is 1, 2, 3, and 4. So here are the 3 types of basic parameters what I've explained. Next, moving on to the lemma and theorem. So these are the lemma and theorems. So we'll move on to the. So these are the 2 books which we can refer for the domination. This is a very good book, Fundamental of Domination in Graph, written by Hines, Hedetnemi, and Slaughter. And the other book is Domination in Graphs, which is again written by Heinz Hadatnimi and Slaughter. So these two books are very easy to understand books. The concepts are very clearly mentioned here in these two books. Easy to understand and easy to make it accessible to you all. So it's already now moving on to the applications on domination. So we can see there are various applications of domination in graph theory. So as the decade pass on, many researchers have found out the applications of domination in graph theory. Many of them has make it happen, like in matching theory, labeling of graphs, algebraic graphs. Some of them have found out the applications in engineering, physical, social, and biological sciences. Many of them have found the applications in linguistics. And there are a stupendous development is seen in this theory of graph, in this graph theory, because of its far-reaching scope in algebraic, optimization, and computational issues. So moving on to the next slide, I'll show you how dominations are very much useful in every field. Graph theoretical ideas usually utilized in OR, operation research. Okay, so next here. So this is the basic application of domination set, whereas in school bus routing, most school in the country provide school buses for transporting children to and fro from the school. No bus ride can take more than some specified number of minutes, and limits on the number of children that a bus can carry at any one time. So here in this simple graph, we can see that if a bus is traveling from one route and it's reaching to the school, so we can make sure that the bus should pass to the route only once. It should pass only once. So here the domination set, how it is important means, it will start from the main point wherein it will reach to the maximum areas, it will reach to the maximum points, or we can even say in a graphical manner that any vertex which dominates to other vertices more number of times. So this graph routing also, this school bus routing also has application of domination set. With this application, we can construct a route for the school bus that leaves the school, gets within the 2 blocks of every child, and return to the school. Then we have computer communication networks. We can see that how computer communication networks are based on the graph theory, and many computer science, electrical engineering, game theory, social media analysis, and fundamentals of network theory offer a powerful mental model to increase our understanding of modern system. So we can see through this how we are connected to each other through mails, through Gmails, through messaging apps, through social media networks, through other type of social media apps and social media sites. Next is the radio stations. So we can see the widely used application of graph theory and domination in these radio stations. Now, modeling of biological networks, even we can see the use of graph theory as a modeling tool in biological networks, and its utilization in the most graphical invariants in such a way that it is possible to identify secondary RNA motifs numerically. Those graphical invariants are variations of the domination number of a graph. So we can see that how the secondary RNA can be identified using graphical invariants. This is the most powerful tool. Graph theory has been a most powerful tool in modeling the biological networks as well. So here we can see the social media networks, how we can use this graph theory. So how we all are connected to each other. In Facebook, we can see the number of suggestions we get from a friend request. Now, if a friend is mine, she has 20 friends of her. Then friend suggestion will come on my page. There's so many friends we can add. So it's all a network, how we are connected to each other through this graph theory. through this graph. So we are all connected to each other. Dominating sets can be used in modeling social networks and studying the dynamics of relation among numerous individuals in different domains. This social network is a social structure made of individuals which are connected by one or more specific types of interdependency. This type of social networking, we can see that it's a very common in these days, and we all are connected to each other by one or the other means. So here also we can see that the location, how we are connected and how the location are being tracked in through the social media apps, and by through this connection we can make out how where the person is and how we are connected to each other. And facility location problems. So these domination sets in graphs are natural models for facility location models in operation research. So in this way, it facilitates, optimizes a certain objectives such as minimizing transportation cost, providing equitable service to customers, and capturing the largest market share. So this also help. This is also a most powerful application in location finding. So moving on to the future works, then these are the references. So the future work, we can see that the Weising stated his conjecture is perhaps the biggest open problem in the field of domination theory in graphs. So whoever are planning to do the future work, so they can work in the Weising's conjecture. So the corollary of this result is that it holds for all graphs with domination number equal to 2, graphs with domination number equal to 2 packing number. Then in 1995, Hortnell and Roll established Weising conjecture for a larger class of graphs called type X, which is an extension of BG graphs. So here, most recent related Weising conjecture was by Brazier and Roll in 2009, which defined the fair domination number of a graph G. So they have proven this true for all classes of graphs. So this can be done as a future work for all the new researchers. These are my references.
Okay. So I think it is
So
over
is
from
there
this
any
recording.
questions?
Yeah, is there any question from the
Are there
participants?
any questions?
This was very demanding topic.
Yes, sir. It's a very demanding topic, and many like from the last decade, many research topics have been studied
Many
on
researchers
domination.
yes, yes, yes.
Yes, sir.
Many
And
researchers are
many new
working on it.
parameters are being found.
Yes, yes. One question is from D. Jayanti. Uh, do you have any idea of topological graph theory? Ma'am, one question is this one.
Yes, sir. I need to check out with the topological graph theory. Actually, I have not into topology till now.
No
So
issue, ma'am. One more
I'll
question.
study
Application of graph theory in AI.
in AI, artificial intelligence.
Yeah.
It's a
Yes, yes,
latest
ma'am.
and hot and trending topic, artificial intelligence. So as of now, I don't see any such applications in artificial intelligence, but I can make sure that there are in every field in real life or any other streams, we can see some or the other applications of graph theory.
I like to add one thing that yeah, application of graph theory is there in the AI as well, because we used to make the combinations in the AI, because AI is nothing but the linear combinations. It makes the linear combinations of many things. So with the graph also we can make it. Okay. So
Yes,
what
sir.
are the books you suggested for domination?
Sir, there is one fundamental of domination in graphs by Highness, Hadatnemi, and Slaughter. and one more is fundamentals in graph. There is also one more book, sir. I'll send you in WhatsApp group. I'll send the book name. It's by F.
Okay, ma'am.
Harari. That is also one more very good book, which I always suggest to my students to refer. It's F. Harari. Harari is the author's name. It's a very good
Okay,
book.
ma'am.
Actually, it's very bit costly book, but if
Okay.
anyone want from me, I can give it to them. They can
Okay.
get a copy of that.
I think Dr. Kamal, your answer is over. Okay, is there any other question? Okay, I think it now. Purnika, are you there?
Yes. So
Yes, so you
thank you,
can.
ma'am, for delivering such an insightful and engaging lecture on
Thank you.
domination and graph theory. Your expertise and passion for the subject is truly thorough, and we are grateful for the valuable knowledge that you have shared with us today. Your
Thank you, ma'am.
comprehensive explanation and practical examples have provided us with a deeper understanding of the topic. Your research accomplishments and achievements in the field of graph theory are truly commendable,
Thank you, ma'am.
and we feel privileged to have had the opportunity to learn from you. Thank you, ma'am.
Thank you, ma'am. I'm overwhelmed to join this workshop and looking forward for more such workshops or conferences from your side.
Okay, sure, ma'am, sure. Okay, I think this is the fifth and final day of this workshop, and I would like to call our. You are not joining. Okay, so our HOD will join within 1 or 2 minutes. So we need to just wait for 2 minutes. Is there any question from the audience? Then you can ask. Uh, because on the first day we have started with uh, graph coloring, I guess, huh? And then the second day we got the topic of cloud computing, and third day we have fuzzy inventory model with the uh, machine learning. These and today is graph application of graph. You have seen that we have taken different subjects in this workshop, because this is the national workshop on applied mathematics and computing. So I hope all the participants, all the students, faculty, colleagues, all of us, we have learned from this, too much learned from this workshop. So I think HOD sir will join now. So sir is facing somewhat problem in joining. So, but he is with me. I am handing over to our head of the department, Dr. Vikash P. Shinde sir, uh, for the concluding remarks.
Thank you, Atul sir. We are grateful for our participants and eminent speakers. They have devoted a lot of time for us, and I hope the participants received so many information from this workshop, especially in the area of the graph theory, cloud computing, and the fuzzy. So, lot of research is going in this area recently, and they are motivated and enhance their knowledge by attending this particular workshop. And in future, we will also try to make it more give more exposure to our participants in the upcoming trends of the latest technology and the new fields. So with these words, I am very thankful to our department, faculty, and especially Dr. Atul. He has given lot. He has put his very sincere efforts to uh, complete this workshop. And nowadays the department is already busy in the NAEC team visit. Our the department, our institute is going to be facing the NAEC team visit on 23 and 24 June. So recently we are very busy. In spite of that, we are already designed this workshop into the month before. So this is very challenging for the Atul. So, but anyhow, he has completed his job and very sincerely has put his full efforts. And I hope the all participants get good knowledge. And if they have any remarkable suggestions for improvement of this workshop, they may welcome. Any suggestions? Okay. Once again, thanks to all.
Okay, I would like to thank our HOD, head of the department, and also along with me, our members, student members have also helped me a lot in conducting this workshop. Everyone in the team, from part to last Purnika, everyone has performed their work that is assigned to them. So I'm very uh, grateful that I got such team for conducting this workshop. So I'm thankful to each and every uh, member who joined in this workshop. And last but not least, all the participants, because without the participants, no workshop will be means it will be a successful. So I like to thank all the participants as well. So finally, is there any suggestion from the, because the head of the department was asking that is there any suggestion for the upcoming workshops we will conduct. So is there any suggestion you can give in the final feedback form? So the feedback form will be shared with the by Mradul and Ananya. So they will share with you soon, and Vikram also. So I think it is already shared in the chat box. You can see because today there were two sessions, session 5th and session 6th, from 4 to 5 and 5 to 6, and one more feedback will be shared with you all, final feedback of overall 5 days. So that form also you need to fill. Okay, so one more thing I need to clarify that the participants who have attended at least 4 sessions out of 6, uh, they may get the certificates, but or also quiz will be checked for all. So those who qualify this, they will get the certificates. Those who have attended only 1 or 2 sessions or 3 sessions, I'm sorry for sorry to them. Okay? They will not get the certificate. So this was one clarification from our side. Uh, and officially now I like to conclude this overall workshop. We are very thankful to our speakers who have accepted our request to give the this wonderful lectures, and all the participants as well. Okay, thank you so much. Thank you everyone for being with us in this journey. Thank you. So we are ending the session officially now. Parth?
Yes, sir.
Yes, sir. Thank you, sir.
Yeah.
Thank
Thank you.
you, sir.
Thank you everyone.